Got a question here that comes up reasonably often, and it's asking us to prove the differential routine of transforming x cubed into 3x squared by, the power multiplying by the coefficient and then reducing that power by 1. And we've got to prove this from first principles. So let's have a go. So I've got the function y equals x cubed, and I've drawn it on a grid. Okay, the proof goes this way. If we choose a point on the x-axis, let's choose it there, and let's call this point x. What's the corresponding y value? Well, if x is our x value, y is x cubed. What about a different x value? What about this value? And its corresponding y value. I could call that x2 and we'd get x2 cubed, yes, but in this example, let's call the difference between the x and our new x value, let's call this h. So this is x plus h. So this value up here is x plus h cubed. Now suppose I draw a straight line through our intersection points, let's call them A and B. So what would the gradient of that line be? Well, the gradient is rise over run, which in this case, the rise is this y value minus this y value. So it's x plus h all cubed minus x cubed. And this is divided by the run. Well, the run is simply h. We've got to multiply this out. Well, the multiplication of this is a quadratic and then multiplied by x plus h again. So the quadratic, it will be x squared plus 2xh plus h squared. And that will be multiplied by x plus h minus x cubed, and that's all divided by h. We've got to multiply this out. We multiply everything in this first bracket by x, and then multiply everything in this first bracket by h. So this is equal to x cubed plus 2hx squared plus h squared x. That's the first three terms. Now multiplying through by h, and I get plus hx squared plus 2h squared x plus h cubed minus x cubed, and this is all divided by h. Straight away, the two x cubed terms cancel each other out. So gathering up what's left, the x squared terms, we've got one here and we've got one here. So we've got 3hx squared. Now the x terms, we've got one here and we've got another one here. So this is plus 3h squared x plus h cubed. And again, this is all divided by h. So now dividing through by h, we get 3x squared plus 3hx plus h squared. And that is a perfectly good description of the gradient of AB. Now here comes the clever bit. Supposing I grab B and start moving it towards A. The yellow line will compensate but still reflect the gradient between those 2 points A and B. The main point is that H starts decreasing, and as B approaches the point where it touches A, H tends towards 0. When B is pushed right onto A, H indeed does become 0. Now what happens to the gradient? Well, if H starts tending towards 0, this term here and this term here will also tend towards 0. So if we write that down as B is pushed towards A, H tends to 0. And the gradient of AB tends towards 3x squared. And therefore, when h equals 0, it's not now the gradient of AB. The gradient at A is equal to 3x squared. And that is your answer. So the yellow line that used to be the gradient of AB now becomes the tangent to the curve at A. So now we can actually give a value to the gradient at any point on the curve by just putting in different values of x. So the cubic's gradient function is a quadratic. So there we are, differentiation from first principles.